Hello and welcome. We hear the term machine learning thrown around constantly. It sounds like magic, but today we're going to peel back all that hype and get right to the core of it. What does it actually mean for a machine to learn? We're going to figure it all out together, and we'll do it using a simple and kind of delicious example.
So let's just start with that one big question. When we say a machine learns from experience, what's really going on under the hood? I can promise you, it's not magic. It's actually something way more interesting. It's a logical process. But, as we're about to find out, it's a process that has some really surprising and pretty profound limitations.
And our entire journey into this huge, complex field, it all begins right here. Seriously, forget about algorithms, forget about big data for just a second. I want you to just picture a papaya. This one fruit is going to be our guide to understanding pretty much everything.
Okay, so here's the setup. Imagine you're on a beautiful Pacific island, and papayas are everywhere. But there's a catch. Some of them are incredibly delicious, and others will make you really sick. Your job is to figure out how to tell them apart before you take a bite. You can check things like their color, how soft they are, and you learn from your past experiences, right? From the ones you've already tried. Believe it or not, this is a machine learning problem in a nutshell.
Now, this whole papaya problem lines up perfectly with how machine learning actually works. So first up, you get your training data. This is just your basket of papayas that you've already tasted and labeled, tasty or not tasty. Then, and this is a really crucial step, you define what's called a hypothesis class. This is you deciding what kind of rule you're even looking for. Are you looking for a circle, a triangle? For instance, let's say you decide to only look for simple rectangles based on color and softness. Step 3, you learn from the data. You look at all your examples and pick the one single rectangle that does the best job explaining them. And finally, you predict. You take that rule you just learned and use it to pick your next papaya.
So how do we find the best rule? Well, the most obvious strategy seems pretty simple, right? Just find a rule that makes the fewest mistakes on the papayas we've already seen. Sounds logical. This strategy actually has a formal name, and it leads us straight into our first big, dangerous trap. It's called empirical risk minimization, or ERM for short, and all that fancy name really means is minimize your mistakes on what you've already seen. So if you can find a rule that perfectly explains every single papaya in your basket with 0 errors, ERM says, yep, that's the one, go with that. It's intuitive, it makes sense, it feels right.
So you do it. You find a rule that flawlessly categorizes every single papaya you've ever eaten. You have a perfect track record. What could possibly go wrong? Well, it turns out pretty much everything.
And this brings us to what is maybe the single biggest villain in all of machine learning, overfitting. This is the trap that our simple, common-sense ERM strategy just walked us right into.
Imagine for a second you don't limit yourself to a simple rectangle. Instead, you let your rule be this insanely complex, squiggly line that perfectly snakes its way around every single data point in your basket. Your error rate on that past data, it's a beautiful, perfect 0%. But what happens when a new papaya comes along? That wiggly, over-specialized rule is totally useless. It wasn't learning the true pattern, it was just memorizing the random quirks of your specific basket. So your error on future data is going to be huge.
At the end of the day, what you've created is a rule that has memorized the past instead of actually learning a general pattern. It can explain your history with perfect accuracy, but it's completely awful at predicting the future. That, right there, is the textbook definition of overfitting.
So our simple ERM learner failed because it just got lost in all the details. To have any chance of success, it needs some kind of constraint, something to stop it from chasing those crazy squiggly rules. It needs a bias.
In machine learning, we call this an inductive bias. It's basically a set of assumptions that you build into the learner before it ever sees a single piece of data. So instead of letting it search through every rule imaginable, you restrict it. You force it to only look within a smaller, simpler set of possibilities. And that pre-approved set of rules, that's our hypothesis class.
So for our papaya problem, this means we tell our learner, look, forget about those complicated squiggly lines. You are only allowed to look for simple rectangles. Now go find the best one of those. Just by restricting the search space like that, we make it much, much harder for the learner to overfit the data.
And this brings us to maybe the most fundamental balancing act in all of machine learning, the bias-complexity trade-off. On one side, you have simple rules, like our rectangle. We say these have a high bias because they carry a strong built-in assumption about how the world works. Now, they might miss some of the finer details, but they are way more robust and much less likely to overfit. On the other side, you've got complex rules. They have low bias. They don't make many assumptions. They can fit your training data perfectly, but they are living on a knife's edge with a super high risk of overfitting.
Okay, so we've learned that we need to pick the right bias, the right set of simple rules for our problem. But that leads to a really interesting and kind of humbling question. Could there be one perfect learner? You know, a learner with the perfect built-in bias that just works best for every single problem?
Let me put it another way. Is there a master algorithm out there? Could we design one single universal learner that you could throw any problem at, papaya tasting, filtering spam emails, predicting the stock market, and it would just always be the best?
The answer, according to one of the most foundational theorems in machine learning, is a simple, stark, and powerful zero. There are exactly 0 algorithms like that.
This is famously known as the no free lunch theorem, and what it proves, mathematically, is that no single learning algorithm can be the best on every possible problem. For any algorithm you can come up with, no matter how clever, I can invent a learning task where it will fail completely, while some other different algorithm will knock it out of the park.
Now, why does this matter? Well, the implications are huge. It means there is no master algorithm, no single key that unlocks all of our problems. Every algorithm is a specific key designed for a specific lock. Real success in machine learning isn't about finding some magical, all-powerful algorithm. It's about understanding your problem so deeply that you know exactly which key you're supposed to use. So, if you take one thing away from all this, let it be this. The goal isn't to find the one best learner. The real goal is to become an expert on your problem so you can pick the right tool for that specific job. Our little papaya learner, with its bias for simple rectangles, would be fantastic for the papaya problem, but it would be absolutely terrible for trying to identify a complex spiral pattern in data.
And that leaves us with one final and really critical thought. The no free lunch theorem tells us that every single algorithm has a blind spot, a type of problem it's just fundamentally bad at solving. The entire art and science of doing machine learning in the real world then really just boils down to this. How do we choose the right one, and what happens when we get it wrong? Answering that is what it's all about. Thanks for joining me on this explainer.